Welcome to Temple of Pwn, Part 12. This week we'll talk about Ret2CSU or not Ret2CSU, Ret2DlResolve and how that is, what it's about, and how it works and how we can use it. So, DL runtime resolve is the function that's usually called for dynamic loading of a function. Usually, when you get to the GOT, there's just the function itself isn't there when it's first called, so it actually has to resolve the address for it, and then it'll store the function address itself into the GOT. This is used when full rel-row is not enabled, so partial or no rel-row, which means the GOT is writable. And it uses several structures within the file itself to locate and resolve these functions. We'll go over that. And then overall, pretty much the runtime resolve just finds the function based on the string, and there's nothing else really to it. Just give the string name, and then it'll figure it out. So, as I said, the GOT originally points to a lookup function, or kind of how it is, points to a lookup function. So when a function's first started, it usually has a function pointer to like a PLT lookup address. And in this case, 4030 just pushes 0 and then jumps up to this actual address, which pushes the 0x4008 address, or value that's at that address, which is going to be I believe, a binary structure pointer. Don't quote me on that though. And then it'll jump to the 4010, which are the value that's at that address, which is actually going to be the resolve or DL resolve function itself. And then the interesting part about this is that it actually uses the stack even in a 64-bit context. Here, this is a 64-bit binary. We can see it pushes 0 and then pushes the value that's at that address. That's mostly because when you resolve a function, the registers will usually hold what's actually going to be called at that function, and we need to be able to keep that when we actually call our function, so we can just call the function with the parameters we actually need instead of messing them up here. Hopefully that made sense. But anyways, so how it actually resolves. So there's a jump relative structure, there's a string structure, and there's a symbol structure. So here's the kind of layout of the jump relative structure. Here's an example down here. Inside the elf, it'll be at this address. Usually won't be the same. It kind of depends on how many functions and how it's kind of compiled, I guess. But we can see we have 3 different 16 or 8-byte values. And the first one's going to be the R offset, which in this case will be 404018 hex for free, and that's just going to point to the GOT location of free, so when it actually resolves it, it knows where to write back to the GOT so you can use it for the future. Our info will be 8 bytes. This will be this value. The first 4 bytes are pretty much a function lookup value, I'm pretty sure, because if we change that, it kind of gets angry. And then the last 4 bytes are an index into the symbol table. So here, I'll show you in the next page, but for free it's 1, and then R added is 0 for all these. I'm not really sure at the moment what that's for, but as long as we just keeping it similar to what it's at, then we can just set it to 0 and should be good. But in the symbol table, if we look and we looked for free, we can see that symbol table starts here and free is at index 1. Symbol table always starts at index 0, and that's just to make sure that I'm pretty sure the lookups work correctly, so it doesn't look up 0 or something. Don't quote me on that. But anyways, the symbol table has this kind of structure: 4 bytes, 1 byte, 1 byte, 288, which is the name offset, info, other. It's actually what it's called in IDA. The item's just other. Maybe it's a saved byte for something in the future. SHNDX, value, and size. For most of the time, in our instances, these are mostly going to be 0 for the last 4 items. But the first one is 79, and that's going to say the number of bytes from the string table is where the actual name of the function that this symbol points to. And then info, I'm not sure what info is for. We'll probably set that to 0 in our case, but because at first I thought it'd maybe be the length of the name, but that doesn't really line up for free with 12, and all of these are also 12, so maybe it also just says that this is going to be a GOT entry instead of, like, standard out, standard in, standard error aren't actual functions, and they're not going to be the GOT, so maybe that's why. And Gmon start isn't in the GOT either, I don't think. Anyways, it doesn't matter for us really. And string table, we can just see it's a string of x bytes. So if we went in here and then went in 0x79, AB1 will get free. And we can see that that kind of points forward like the symbol table should. So here's just the kind of top to bottom entire step by step. So the PLT will call the lookup function. It'll push or it'll go to the GOT pretty much, grab that address, and then when it goes back to its own PLT kind of lookup section, because each function will have a different address, it pushes its own index into the jump, or the index in the jump rel table onto the stack. It holds the jump rel table will hold the GOT address to overwrite, has the lookup type, i.e. is it a function, and is it a function or is it just a pointer within libc or something? And it also had the symbol table index. The symbol table itself holds the function name offset, which is what we care about in the string table. So the way we can exploit this is if we're able to create a fake jump, symbol, and string tables with custom offsets so everything lines up, we can call whatever function we want by spoofing kind of a lookup. And to make this happen, we just need to know some offsets. So we kind of need to have leaked memory or have pi off. We need to have writability somewhere. It could be in the heap. We just need to know the offset to where we're at. And then semi-stack control, because we need to be able to call the lookup function with our offsets in there, and then that's pretty much it. And if you're interested, the original kind of write about this is from a FRAC article, issue 40 or 58, and it's from 2001. So it's almost 20 years old. It'll be 20 years old in December, and it's still possible to use today. Hasn't really been big as far as I know, except for in the past 5 to 10 years. But it's still kind of important because it's a useful technique if you don't have a leak and you're able to get some kind of writing ability going. So with that, we're going to look at this challenge called No Output from a CTF this last weekend. I think it was the DarkCon one, but this challenge is called No Output, so you can kind of assume what we're working with. As you can look, if you looked through the functions on the side here, I'm not sure if anyone in Discord will be able to see it, but there's no functions that actually write to the user. It's all just reading, and that's kind of a problem for us if we want to leak a memory. So we're going to use our Ret2DlResolve to resolve system without actually having to leak anything to us. So to start out, inside this init function, zoom in a little bit, it looks like we just read in 47 hex characters into probably a 30 hex, oops, just moved that one in accident, 20 hex buffer, and then, so there's a blatant overflow right here, but there's also a stat canary, so if we overwrote that at all, it would just crash on us, and we don't really have anything to work with that. So after init, we get a scanf. Get int format is just %d. Get char, so it reads a number between 3, 1, and 2. If it's anything else, it'll call exit. If it's greater, if it's 0. Yep, so if it's anything else, that's actually interesting. What if it's, oh, right here. Oh, yeah. Anything else, it'll call exit. Instance will check out add. Looks like it'll grab an index from us, scanf, signed, so it can't be negative, 4 or 15 or higher, so 0 through 15. Then it looks like it just returns that value. Get valid size, can't be signed, 0 to 100 or 1000 hex, so 0 and 4096 is our size we can get. Looks like it just straight mallocs it. Looks like it saves our valid size into a pointer, like a chunks length. So it looks like an array of chunks length is right after our array of actual chunks. So once it mallocs it, it'll probably save in the chunk. Yep. Then it looks like it reads based off of our chunk length, or if it finds a new line. So just keep reading until it hits the chunk length total, or hits a new line. So no overflow there, it doesn't look like. Edit. Get index. Doesn't ask us for a new size, so it's based off the chunk's length again. Pretty much the same thing as add right there, nothing different to it. Delete, get index, they're all going to be the same. Grabs our chunk, make sure it's not 0. We'll try to free it, but it doesn't look like it ever zeroes that chunk back out, so it looks like we have a use after free right here. And that's kind of it. So we can use the delete with the, or delete a chunk, do a use after free with the edit to just overwrite a chunk, and then with that we can pretty much just get a Tcache chunk anywhere if we're working with Tcache, or if we're working with an older libc that doesn't have Tcache, we could probably do an unsafe unlink to get into the chunk pointer, and we're able to do this because based on the actual address of the functions and pointers, it looks like there's no pi on this binary at all, and we can double check that. Here, we'll go checksec, no output. Yep, there's no pi, it's at 0x400,000. And then from there we just go on. So I have 2 exploits here already. One is going to be a simplified method, I guess, and the other is just going to be a by hand, because PwnTools likes to give you methods to just get this done easier. So I'll show you both, but first let's do template to custom.py. So here we have our template. Send2 is just without the new line. Add just 1 index size data, 2 index size or index data for edit, and then delete with index and data. So first we'll probably add 2 of them. Let's go 100 bytes. Go A. Let's get that Tcache chunk working. So delete 0, delete 1, and we just check to make sure everything looks right. Did I miss something? Delete should just take the index. I think I had this problem earlier and I just didn't fix it in the template. Delete 0, delete send 3. So it was already dead by then. Oh, I don't have a 1. Yeah, that should work. It did not work. So let's just make sure the chunks were allocated correctly. Oops. What the heck? First chunk. Oh, I forgot about that first init call. We just got to send in some data. So let's call this test, because it's going to read in that 47 hex characters, or 47 hex bytes. There we go. So if we look at our heap bins, we should see that we have 2 chunks right here. And if we were to just edit 0, which is 2, 0, ASDF, should be able to see that we have a corrupt chunk. Yeah, I think I just added 0 instead of 1. That's fine. So we're able to get the Tcache pointer that way. We know what the local libc version is because I'm running it locally, and it's going to be 2.31. But if you didn't, you'd probably do some remote testing to see if Tcache bins were allowed, or if they had some kind of, or what, if you were using an older libc version, you could just do a unsafe unlink like I said, but probably could do an unsafe unlink no matter what. Might be a little bit harder though, getting the chunks to line up correctly, but I think that should work for any version. We're just going to go with the Tcache just to be safe. Let's change the order of that. We'll edit 0 and go P64 of the address of chunks. So you just want the chunk address there. Chunks is located at chunks 0x4040C0. Then if we allocate 2 chunks, the next, if we allocate that chunk, and then this chunk right here should be allocated over the chunks array itself. We'll put it at 10 so we don't overwrite it itself. And then we'll put just A times 8 plus B times 8. Go check it out. And then we see our chunks are correctly overwritten. And our 10 one is still here. So if we were to actually do it at 1, we'd be overwriting it. And I think the way it's reading in data is that, it's grabbing the chunk every single time. So if we were to put one byte in here that's not pointing to itself, then it would incorrectly kind of jump all over, because it's going to be a partial overwrite of trying to grab a chunk that it's, or the address incorrectly. So it's just safer to go with 10 instead of, or something. Next, we can do so what we need to do is pretty much be able to write somewhere so we can put our fake tables, and then a way to get to those tables. So first, let's do a write to the table. Go P64 of, we'll call this table underscore adder. Put that at 0x404200. Pretty much anything past the chunks or the chunks size should be fine. We shouldn't have to worry too much. We're going to have to put this to table adder. And then one more thing we're going to have to do first is to actually edit the table adder. We're going to have to just put an allocation at that address because it uses this chunk size, and we're not going to be overwriting the size itself. So we need to make it look like there's actually a chunk at that address, so a size is valid and we can write to it. Next, we can just write to that chunk, so edit to, we'll just call it all, oops, not all, let's call it fake, and then create the fake up here. So let's go fake table, or fake jump, we'll go fake symbol, and fake string. Let's call them all like this. So if we remember back to our jump table, we need to have 0x18 bytes total. The first one will point to the, I believe, to the string table, or string, was it string table or string offset? Let's look back real quick. Oh, no, it's the got overwrite address. The string's going to be inside the symbol. So we can pretty much put this anywhere. We'll just put it at table underscore adder -8. Doesn't really matter because we're not going to call it again in the future. We could overwrite the actual got with this and then have an infinite call of a function if we wanted, but we're fine with this. Next, we have the 7 plus the offset into the symbol table. So we're just going to do a P32 of 7 plus P32 of question mark, because we don't actually know the correct offset from the original symbol table yet. Then P64 0, because we're going to need the, what was it called, R addered, but we don't care about that. So fake symbol table, go check this out. Have the name offset from the symbol table, and then we just put 0 for the rest of them. Yeah, so we just do P64 question mark, because we don't know right now, and then plus P64 of 0 times 2. That should work. Actually, I don't think this, no, that should be fine, because I was thinking that possibly we could run into the problem that the symbol table won't be at an even 10 hex offset, but I don't think that matters with the symbol table as much as it does, as much as I think it does. Checking IDA real quick. Relocation table goes to the symbol table, and yeah, it doesn't matter because other chunks are also at different offsets. So don't need to worry about that. So, and then the fake string, we'll just say is system. I'll put a null byte at the end. Just backslash, I guess either or works, whatever. And then I'm actually going to do a, that should work. This will be 8, and then we'll put bin sh here as well, so we have bin sh available to us. Oops, not zeros. Let's put 2 zeros there. So there should be 2, 4, 8 characters there. That should be 8 characters there. So that lines up. So to know what the actual addresses are, we're going to need the symbol table offset. So the actual address of the symbol table is located at 0x4003D0. The jump table is located at 0x4006C0, and then the string table is located at 0x400538. And so we can get our offsets. So the offset from the string table to our fake string, which is going to be 0x4002 18 hex here, another 18 here, so 30 hex minus our string table. That should give us that address. And then this one is going to be the index, and each index is going to be 24 bytes, so we have to count for that. So 0x400218 minus 0x4003D0, which is a symbol table, divided by 24 bytes, should give us the correct index. And then lastly, we're going to need our jump table index, which is going to be similar to the system table. We'll take take our table address actually, so we have that now, minus our jump table divided by 24, and that should give us our jump table index. So if we edit this, make it fake, we just do fake is equal to fake jump plus fake, not Jake, fake symbol plus fake string. Should give us our entire fake. Now let's just check it out to make sure it all looks right. Out of range. I'm guessing I missed a 0 somewhere or something. Which line was it at? It was on line 47. So in this one, table adder minus 8 would be the right position. That looks fine. P32 of this should be fine, I believe. Oh, no, not right here. This is going to be negative. Oh, yep, these are definitely wrong. 4 there, and a 4 there. We went right to the data section, not the, or the BSS, not the text section or whatever. So that's good now. We check out our address, 0x404200. Don't need that. We check this out. It's going to be the got right. This all looks fine. Our string offset, and then our strings themselves. Perfect. So now we need a way to actually get to this. And we can do this by using our ability to pretty much write to anything. So we can overwrite the got to actually call something to give us some stack control. And if there's a function that we actually know gives us stack control, because there's a buffer overflow in the init function that we looked at earlier. Right here. So the problem with that was that the stack check fail will call. But if we were to overwrite the got address for stack check fail with just a ret, we'd get back to this leave, and then we'd have full stack control. So let's overwrite. We'll overwrite exit got, because we're able to call exit pretty much whenever we want based on the main, to call init, and inside init we'll do the overflow, and then after the overflow, then we'll overwrite the stack check fail to just ret, and doing so will allow us to just go straight into a ROP chain that will allow us to do our ret to CSU, our Ret2DlResolve. Gosh. So let's edit 0 P64. Let's put a question mark right here because I need to actually make sure those are right. So P64 exit got plus P64 of stack got, and I'm just going to do lazily. Whoops, doesn't like that. That makes sense. Stat got is equal to 0. At this point, I might as well have just looked it up in IDA, but wow, that was... I'm just going to look it up in IDA, because I'm right there pretty much anyways. So, exit is... didn't want to undo it. Undo the undo. And overrode it. Sweet. Exit got is at 0x404058, and stat got is at 0x404020. So that should all be good. Now we check out the got exit should be 0 because we overwrote that with that last edit. We need the address of init also. We can use that down here. Init equal to 0x401236. Init, and then edit 1 to be p64 of a ret instruction. Ret is equal to, well, let's use init's ret, because any ret should work, 0x401282. Whoops. So at this point, if we call exit, so we'll just finish this and step through it. We'll do 6, doesn't really matter, any value that's not 1, 2, or 3 should call exit. Go through this. We need to step into exit. See, we're in it now. Just disass that. We'll break here. We'll send in a bunch of A's so we know we overflow it. Actually, might as well do a cyclic while we're here so we know how much buffer we're actually working with. We could probably figure it out based on the how much the IDA looked like, but we'll just make this way. So we see about to call stack check. We can just call, we step through if we want, but we should see that it just calls ret, so we're just back to the leave. And if we look, we're at this address. So if we do cyclic tech lookup 0x, spell cyclic correctly, so it's at 40 characters. So if we were to send a 6 and then send a times 40, anything after that should be a ROP chain. So what we need from this ROP chain is to have, we're going to call system based on this, so we need to be able to jump to the lookup address, which if I can, should be up here, should be at this address right here. So we're going to call this address, but before we call it, we also want to have our offset on the stack, which would be the jump tab table index that we had. So if we're calling system, we also need RDI. So we'll find an RDI gadget, p64 of table underscore address plus 0x. That's 48 hex, I think. Yeah, so 18, so 0x30, 38 should be our bin sh, plus p64 of, we'll call this lookup. Lookup is equal to 0x40, 10, 20, plus p64 of our jump table index. So all we need is a ROP gadget for RDI, which I have one. Oops, not there. Let's see, I have one right here. Just paste it. It's just a ROP gadget. That's probably in the... guessing that's within the CSU part, but it doesn't really matter where it's at. So step in here. Ooh, we have something wrong. Something dies. Oh, probably connected a GDB right before this just to make sure we're actually hitting it correctly. Looks safe. Finish. Should be inside init. We'll break right here to make sure our route chain is correct. Oops, break there, not print it. That doesn't look correct at all. That looks correct. Oh, it's because we used the ret for the stack failure. Alright, this looks better now. So, pop RDI now points to bin sh, ret to here. This looks all correct, but I think the problem is our address might not be, or our offset might not be correct. We can check that quick. The jump table is at 0x4006C0. We can do plus 0x278 because that's where we're thinking it's at, times 24. And that looks correct. Let me check my notes quick. Symbol table, blah, blah, blah. Yeah, that should be correct. So what is happening when we step through this? Go through DlResolve a little bit. If we just continue. Exit with an error of undefined symbol. So maybe our string is incorrect. So let's check out 0x4244200. Don't need the address. So this should point to our string based off the string table. So go this plus the string table itself was located at 0x400538. So that should be system. Yeah, it is. And then the 298, check that out quick. Symbol table is at 0x4004, nope, 3D0, plus 0x298 times 24. Don't need that, we want x/16gx. Oh, it looks like we're off by 1. Yeah, because we want 40, 42, 18. But that looks like it is using 40, 42, 18 minus 3D0. So why did that just now come up as 0x44200 298. Oh, that wasn't, I don't think. Yeah, so that looks right. But if you times it by 24, you get, oops, don't want G, but GX. We're off by 1. So we could just add 1, but I'm trying to figure out why our index is off by 1 in the first place. And I can't think why it would be. Maybe it has to do with it being indexed. No, that's not it. Well, anyways, I guess we'll just add 1 to it and see if that works. Did not work. So I'm going to have to look through my notes a little bit more carefully. Might have to move some stuff around also. So that's the string table. It should be the symbol table. That should be fine. That should be fine. Plus 7 plus string table. I wonder if it's the symbol table, but that shouldn't be it. Check this out quick. So everything here looks correct. Not sure why I wrote this in when I had sitting table there, just to make it look red or look better. Symbol table should be good there. Maybe I have, nope, that looks right. The only difference between my notes is I have it lined up like this, which means I just need to move some stuff around. The stream table is now at that, and then this is going to be plus 0x10. Oh no, that's just the got address, that doesn't matter. This will be 0x10 minus the symbol table. So the thing I'm thinking was the problem was that this wasn't at a 0 offset, but based on the other symbol tables, that shouldn't be a problem. So I'm not sure why that would cause anything. If this still doesn't work, we'll have to walk through the... Oh, that's not going to work because we changed our index now too. Index, this should be at 0x, this is 10, 28. I'm just going to pad this one out another 8 to make it 0x30 even. Go plus 0x30, and we'll just print it to make sure. We shouldn't need to. Continue. Ooh, okay, that's a different error. So assertion failed. Some stuff that I don't know what it's... has something to do with the values after... I thought it was this one, but that's not right. 4010 minus the symbol table divided by 24, 0, P64, 0. String table, which all these addresses should be correct. 538, 3D0, which makes me think my index is incorrect. Index should be 0x4230 minus the jump table divided by 24. That looks right. Oh, this isn't right anymore because I moved all these around. Gosh, guess I could have just kept whatever. Fake string plus fake symbol plus fake jump. Let's try that. 0x7 not found. Okay, so yeah, that looked like it worked. It just that we didn't change our bin.sh offset. And we saw that system was called. Would have been a lot more interesting if it worked the first try, but this should still be good. So I'll step through it just to show you that it all works. Whoops. And I finished them too many times. So there we go. We got a shell from calling the lookup for it. Now that we've done this by hand in the hard way, I'll show you there's a Pwn Tools way. We need to set the architecture first. Context architecture or arc is equal to AMD64. And this just to make sure that it correctly sets up the table, because between the 64 and 32-bit, the only difference really is the size of the tables and just some offsets. So more or less, we can comment out this part. Just get rid of all that. And then from there, I'm just going to copy most of it because I don't just have it all off the top of my head. We can just say DlResolve is equal to Ret2DlResolve payload. We're going to need an elf, so we'll call the elf is equal to our binary, no return. This will help it look up the actual tables it needs. So elf symbol we want is bin.sh, or not bin.sh, system. And then the arguments we want is bin.sh. You could set up more arguments. This is just mostly for the wrap chain to, or not the wrap chain, but yeah, the wrap chain. I think, oh, I should have looked this up earlier, but we'll just go blind. We can say wrap is equal to a wrap chain. I think that's how it's done. Oh, we need to set it to elf. Okay. Elf, do wrap dot Ret2DlResolve and give it the DlResolve. I like to just print the wrap dump just to see what it's working with, because I think at this point it's not going to realize we want it at 0x4200. It's going to put it somewhere else. So I'll just print it out to see where it actually thinks it's at. Arg keyword needs to say equal. Args equal. Elf no return. Oh, it's not no returns, no output. So here it thinks it's at 0x4E00 instead of the 200. Guessing, let me do a quick check. Pwn tools, Ret2DlResolve. Guessing there's a way to set the address. Let me look though. Not the wrap one, I just want Ret2DlResolve. Should be an actual module for it. Just need to figure out where it's at. Because it's using it right there. No, it's using it right here. Ret2DlResolve payload. It's not a part of ROP though. Or maybe it is. Be interesting if it was. Maybe it's just nested within it. Oh. So yeah, it doesn't look like you can actually set the... No, it's right there. Data address. Okay. Well, let's set it then. We'll go data underscore address is equal to 0x404200. I think that was everything. Yeah. So if we were to run it now, we should get it at that address. That looks good. And if we want to put it in there, we need to edit this. Instead of fake, we'll say DlResolve.payload. And then from there, we'll change up our wrap chain just to have the wrap chain they gave us, and do wrap.chain. I think if we get rid of this exit, we should be good to go, because everything else should be the same. Oh, gotta do plus. And if we continue, we should have another show the same way. So there's no difference between what's actually getting written to memory. Not quite sure why this didn't work. Maybe there's... Could be just that it wasn't on even offset. The Ret2DlResolve payload makes sure that everything starts at a 10 hex offset. So when I had this at 2, that could have been the problem. But I also had this changed around a little bit. So I'm not really sure what the entire problem was there, but either way, you should be able to get it working with either the built-in Pwn tools Ret2DlResolve, which could be a little bit cleaner, but this way you actually know what you're working with where. Whereas here, I think they put binsh after the jump table. Yeah, they had to have, because our chain itself was popping to RDI all the way down here after everything, so 48, just the size of everything else combined. But yeah, I think that's everything I had. Are there any questions?
Yeah, I have a question. So let's say you have a binary with pi,
Okay.
and you're just kind of screwed if you don't have a leak, right? And if you do have a leak, then you don't really need to resolve dynamically,
Yes.
right?
So, I mean, if you have a leak, there's No, yeah, there's no reason to dissolve dynamically. Yeah, for the most part, if you have pi or if you don't have a leak, then in this binary, if you didn't have a leak, you'd probably do something else with the heap because wouldn't be too difficult to get overlapping chunks and then get a libc leak through just an unsorted bin and then do a tcache attack at that with use after free.
Okay, yeah.
But without pi and without a leak, this or with pi and without a leak, this becomes almost undoable. I'm pretty sure because yeah, there's no way to get an overwrite in a location you know. So yeah, good question.
Okay. Thanks.